In math practice for class 9, today we are going to discuss circles with the most important theorems and results and examples explained clearly. So watch the video till the end and subscribe to math practice. We will start with some definitions. Circle. A circle is a collection of those points in a plane that are at a given constant distance from a fixed point in the plane. The fixed point is the center and the constant distance is called the radius of the circle. Circles having same center but different radii are called concentric circles. Also, a continuous piece of a circle is called an arc of the circle. Next, a line segment joining any two points on a circle is called a chord of the circle. And if the chord passes through the center, it is called the diameter of the circle. So it is very clear that diameter passes to the center, so diameter will be the longest chord of the circle. Also, a circle can have infinitely many chords because you can have a chord between any 2 points on the circle. Theorem 9.1. Equal chords of a circle subtend equal angles at the center. So, for the proof, consider AB and CD two equal chords of a circle with the center O. We have to prove that they subtend equal angles at the center, means we have to prove that angle AOB is equal to angle COD. Consider the triangles AOB and COD. OA is equal to OC because they are radii of the same circle. Similarly, OB is equal to OD. Again, they are radii of the same circle. AB is equal to CD is given. The chords are of equal length. Hence, by SSS rule, triangle AOB is congruent to triangle COD. So, by congruent parts of congruent triangle CPCT, we have angle AOB and angle COD are same. These results are used in examples. Now the converse of theorem 9.1 is also true. That is, theorem 9.2 says that if the angles subtended by the chords of a circle at the center are equal, then the chords are equal. So here, suppose if it is given angle AOB and angle COD are equal, we need to prove that the chords AB and CD are equal. So again, in triangle AOB and triangle COD, AO is equal to CO and OB is equal to OD. Why? Because they are the radii of the same circle. Angle AOB is equal to angle COD is given to us. So by SAS congruence criterion, triangle AOB is congruent to triangle COD. Hence by CPCT, sides AB and CD means the chords AB and CD are equal. Now some results which will be useful in the examples. Theorem 9.3. The perpendicular from the center of a circle to a chord always bisects the chord. Also the converse is true. Theorem 9.4. The line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Now other results, the length of the perpendicular from a point to a line is the distance of the line from the point. So if you want to find the distance, you have to find the length of the perpendicular. If the point lies on the line, the distance of the line from the point is 0. The distance of the diameter, which is the longest chord from the center, is always 0. Next, theorem 9.5. Equal chords of a circle or of congruent circles are equidistant from the center. And the converse is also true. Chords equidistant from the center of a circle are equal in length. That means in the first case, if you have a circle and the two chords are equal, then OM and ON, that means the distance from the center will be same. And the same holds if there are two circles with congruent chords. So if again in two circles AB and CD are congruent, here also OM and ON are equal. And if the chords are equidistant from the center, then they are always equal in length. First example. If two intersecting chords of a circle make equal angles with the diameter passing through their point of intersection, prove that the chords are equal. First, let us see what is given to us. We are given AB and CD. They are two chords of the circle with center O and they intersect at a point E. Second thing is here PQ is the diameter and it passes through E, such that angle AEQ and angle DEQ are equal. It is given to us that it makes equal angles with the diameter. So angle AEQ and angle DEQ are equal. We need to prove that the chords are equal, means AB is equal to CD. So first thing is, for the construction, draw perpendiculars OL and OM on chords AB and CD respectively. We have to prove AB and CD are equal, and for that we have constructed perpendiculars OL and OM. Now consider angle LOE. By the angle sum property, sum of the three angles of a triangle is 180 degree. Angle LOE will be equal to 180 degree minus 90 degree, because OLE is a right angle 90 degree minus angle LEO. So now that will be equal to 90 degree minus angle LEO. But what is angle LEO? It is actually angle AEQ. So 90 degree minus angle AEQ. But by given, angle AEQ and angle DEQ are same. So we can write 90 degree minus angle DEQ. But what is angle DEQ? It is equal to angle MEO. So we have angle LOE is equal to angle MOE. Consider this as the first statement. Now consider triangles OLE and OME. So we have angle LEO is equal to angle MEO. Correct? It is given to us. Again, by the first part we have proved angle LOE and angle MOE are equal. EO is equal to EO, common. Therefore, triangle OLE will be congruent to triangle OME. So by CPCT, OL and OM are equal. OL and OM are equal. So by the theorem 9.6, which we have just now seen, that the distance of the perpendicular is equal, so the chords are equal. AB is equal to CD. Now example 2. In a circle of radius 5 cm, AB and BC are two chords of equal length, means AB is equal to BC of length 6 cm. Find the length of the third chord AC. First of all, AB is equal to BC is equal to 6 and radius is 5 cm. First thing is, we draw a perpendicular BM to AC. Now BM is the perpendicular bisector of AC, and thus it passes through the center of the circle. Why? Because we have seen a result, since AB and AC are equal chords, the center of the circle lies on the bisector of angle BAC, and BM passes through the center. Now let AM is equal to Y and OM is equal to X. Consider AM is equal to Y and OM is equal to X. But radius OB is equal to 5 is given. So what will be BM? BM is equal to 5 minus X. Apply the Pythagoras theorem to triangle OAM. So OA square is equal to OM square plus AM square. So putting the values, 5 square is equal to X square plus Y square. Consider this as equation 1. Again, applying Pythagoras theorem to triangle AMB, we have AB square is equal to BM square plus AM square. But AB is 6, so 6 square is equal to 5 minus X whole square plus Y square. Subtract equation 1 from 2, and when we solve it, we get X is equal to 7.5. Putting X is equal to 7.5 in the first equation, we get Y is equal to 24 by 5. Thus, AC is 2 times AM. We know that AC is 2 times AM. So what is AC? 2 into 24 by 5, or AC is equal to 9.6 meter. Next, example 3. Prove that the line of centers of two intersecting circles subtend equal angles at the 2 points of intersection. First of all, let us draw the diagram to understand this. Consider two circles with centers O and O dash, and let the two circles intersect at 2 points P and Q. So now what we need to prove is they subtend equal angles at the 2 points of intersection. Means we have to prove that angle OPO dash is same as angle OQO dash. So now consider triangles POO dash and QOO dash. OP is equal to OQ because they are the radii of the same circle, first one. O dash P is equal to O dash Q, radii of the same circle. Also OO dash is equal to OO dash, common. So by SSS congruency, triangle POO dash is congruent to triangle QOO dash. So by CPCT, the angles OPO dash and angles OQO dash are same. Next important example. Two chords AB and CD of lengths 5 cm and 11 cm respectively of a circle are parallel to each other and are on opposite side of its center. If the distance between AB and CD is 6 cm, find the radius of the circle. So first of all, let us draw the diagram, and remember we are using all the results we have seen before. So over here you have a circle with two chords AB and CD of lengths 5 and 11. O is the center of the circle. Here OM is perpendicular to AB and we can see ON is perpendicular to CD. And OB and OD are joined. Now by theorem 9.3 we know that the perpendicular which passes to the center, it bisects the chord. So over here, since AB is 5, the perpendicular bisects it, so BM is equal to half of AB or 5 by 2. Similarly, ND is equal to half of CD, which is 11 by 2. Now consider ON is equal to X, but we are given the distance between the two chords is 6. So OM will be equal to 6 minus X. Now consider the triangle MOB. So by Pythagoras theorem, OB square is equal to BM square plus OM square. Putting the values, OB square is equal to 5 by 2 square plus 6 minus X whole square. So solving this, we get the first equation, which is OB square is equal to 25 by 4 plus 36 minus 12x plus x square. Similarly, consider triangle NOD. So again applying Pythagoras theorem, OD square is equal to ND square plus ON square. Putting the values, OD square is equal to 11 by 2 whole square plus x square. We have two equations, but we know that OB is equal to OD because they are the radii of the same circle. So equating equations 1 and 2, we get 25 by 4 plus 36 minus 12x plus x square is equal to 121 by 4 plus x square. Solving this, we get 12x is equal to 12 or x is equal to 1. Here x square gets cancelled. Solving it, we get x is equal to 1. So OD square is equal to 11 by 2 whole square plus 1 square. So that gives us 125 by 4. Correct? So what is OD? OD is 5 root 5 by 2 centimeter. OD is the radius. We have got radius is equal to 5 root 5 by 2 centimeter. Example 5. See, we are doing all different kind of examples. So please practice them. A circular park of radius 20 meter is situated in a colony. 3 boys, Ankur, Syed and David, are sitting at equal distances on its boundary, each having a toy telephone in his hands to talk to each other. Find the length of the string of each phone. So now, instead of giving directly the points, they have said that there are positions of 3 people. Let us consider that as points A, B and C on the circle. Since they are sitting at equal distances, the triangle ABC will form an equilateral triangle. Now, AD perpendicular BC is drawn. We construct AD perpendicular to BC. AD is the median of triangle ABC. Why? Because it passes to the center O. We know it passes to the center O. It is the perpendicular, so it will bisect. That means AD is the median. Also, O is the centroid of the triangle ABC, and we know that since O is the centroid, it divides the median into 2 by 3. That means OA is equal to 2/3 of AD. Consider this as equation 1. OA is equal to 2/3 of AD. Now let a side of the triangle be A meters. That means all the 3 sides are of same measure. So let that be A. So now BD is equal to A by 2 meter. Apply Pythagoras theorem to triangle ABD. So AB square is equal to AD square plus BD square. So what is AD square? AB square minus BD square. So AD square is equal to A square minus A by 2 whole square. Solving this, we get AD is equal to root 3 A by 2. Now, by the first equation, OA is equal to 2/3 of AD. That means putting the values of AD, we get this OA equal to 2/3 into root 3 A by 2, which we get it as A by root 3. But now radius OA is given to be 20. Correct? It is given that the radius of the park is 20. Hence, A is equal to 20 root 3. OA is the radius. OA is equal to A by root 3. So, A is root 3 OA, which is equal to 20 root 3. Which gives AB equal to BC equal to AC is equal to 20 root 3. Hence, the length of the string of the toy for each of them is 20 root 3 meters. Again, some important results which we are going to use in the examples. If two chords of a circle are equal, then their corresponding arcs are congruent, and conversely, if the two arcs are congruent, then their corresponding chords are equal. We can see from the diagram. Congruent arcs or equal arcs of a circle subtend equal angles at the center. This is because of theorem 9.1. Equal chords of two congruent circles subtend equal angles at their centers. What are two congruent circles? Two congruent circles are there if they have the same radii. If two equal chords of a circle intersect within the circle, the line joining the point of intersection to the center makes equal angles with the chord. Now we will prove theorem 9.7. The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Remember, this is a very important theorem and it is used in solving the examples. Once again, the angle subtended by an arc at the center is double the angle subtended by it at any other point on the remaining part of the circle. So first of all, suppose you have an arc PQ. PQ is an arc subtending angles POQ at the center O and PAQ at a point A, which is on the remaining part of the circle. What we need to prove is POQ is equal to twice PAQ. It is double PAQ. Join AO and extend it up to the point B. Now angle BOQ is equal to angle OAQ plus angle AQO. Why? Because an exterior angle of a triangle is equal to the sum of the other two interior angles opposite to it. So angle BOQ is angle OAQ plus angle AQO. Now this is important. Consider three cases. Now suppose your arc PQ is the minor arc. That is the first case. Second case is arc PQ forms the semicircle. And third case is arc PQ is the major arc. So let us consider the three cases. The first case, in triangle OAQ, OA is equal to OQ because they are the radii of the same circle. Therefore, angle OAQ and angle OQA are equal because angles opposite to equal sides are equal. But we know that angle BOQ is equal to angle OAQ plus angle AQO. We have just now seen that. So angle BOQ is equal to twice angle OAQ. Similarly, angle BOP will be equal to twice angle OAP. From the first and second case, when we add them, we get angle BOP is equal plus angle BOQ is equal to twice angle OAP plus angle OAQ. But what is OAP plus OAQ? It is equal to angle PAQ. Hence, angle POQ is equal to twice angle PAQ. Now, this we have proved for the first case. Similarly, for case 2 also we can prove the same way. In case 3, where PQ is the major arc, the reflex angle POQ is considered and that is equal to twice angle PAQ. Some other results. Theorem 9.8. Angles in the same segment of a circle are equal. This we can prove easily by theorem 9.7. Since A can be any point in the above result, so we can say that angles in the same segment of a circle are equal. Second thing, angle in a semicircle is always a right angle. How will you prove this? If you consider the second case of the proof of theorem 9.7, which we have seen, in which it is a semicircle, PAQ forms a semicircle. So in that case, we know that since POQ is twice angle PAQ, but what is POQ? It is 180 degrees. So angle PAQ will be 90 degree. Hence, angle in a semicircle will be a right angle. Cyclic quadrilaterals. A quadrilateral ABCD is called cyclic if all the four vertices of it lie on a circle. So if you have a quadrilateral and all its four vertices lies on a circle, then it is a cyclic quadrilateral. Some important result for cyclic quadrilateral. The sum of either pair of opposite angles of a cyclic quadrilateral is 180 degree. Means if you take the opposite angles, angle A plus angle C is 180 degree. Similarly, angle B plus angle D will always be 180 degree. The converse is also true. If the sum of a pair of opposite angles of a quadrilateral is 180 degree, then the quadrilateral is a cyclic quadrilateral. Again, this result is used in examples. Now, we consider theorem 9.9. It is the converse of theorem 9.8. If a line segment joining two points subtends equal angles at two other points lying on the same side of the line containing the line segment, the 4 points lie on a circle. That means they are concyclic. The statement says that if a line segment joining 2 points subtends equal angle at two other points, that means suppose you have a line segment AB which subtends equal angles at 2 points C and D. That means angle ACB and angle ADB both are equal. What we need to show that is the points ABCD lie on the circle. So first of all, let us draw the circle which pass through points A, C and B. We need to prove that D also lies on the same circle. Now, suppose that it does not lie on the same circle. Point D does not lie on the same circle. Then it will intersect AD or extended part of AD at point E or E dash as seen in the figure. If points A, C, E and B lie on a circle, then angle ACB and angle AEB, they will be same by the theorem 9.8 just we have seen. But it is given that ACB and ADB are equal. That means angle AEB and angle ADB are equal. Angle AEB and angle ADB are equal means E and D are the same points. E coincides with D. Similarly, if it is in the extended portion, we can show that E dash also coincides with D. That means D lies on the circle, or ABCD, all the 4 points lie on the circle, or they are concyclic. Example 6. Two circles intersect at 2 points A and B. AD and AC are diameters to the two circles. Prove that B lies on the line segment DC. So first thing, we are given two circles which intersect at 2 points A and B. Also it is given AD and AC are respectively the diameters of the two circles. We have to prove that the point B, it lies on the line segment DC. Now angle ABD is 90 degree. Similarly, angle ABC is also 90 degree. Why? Because they are angles in the semicircle, and we know that they are angles on the semicircle because AD and AC are diameters, and since they are angles on the semicircle, they are right angles. Now, angle ABD plus angle ABC is equal to 90 plus 90 or 180 degree. That means DBC is a line. Hence, B lies on the line segment DC. Example 7. Remember, we are doing many examples because circles is an important chapter. Prove that the quadrilateral formed by the internal angle bisectors of any quadrilateral is cyclic. Suppose we are given a quadrilateral ABCD, and suppose you have the angle bisectors AH, BF, CF and DH of the internal angles AB, C and D respectively, which again form a quadrilateral EFGH. You can see in the diagram. What we need to prove is this EFGH is a cyclic quadrilateral. Means by the previous result, if we can prove that the sum of the opposite angles is 180 degree, it will be cyclic. So first of all, consider angle FEH. Angle FEH will be equal to angle AEB because they are vertically opposite angles. We know that sum of the three angles of a triangle is 180 degree. So angle AEB, we can write it as 180 degree minus angle EAB minus angle EBA. But since we have angle bisectors, so angle EAB is half of angle A and angle EBA is half of angle B. So angle FEH is 180 degree minus half of angle A plus angle B. Now angle FGH in the similar manner will be equal to angle CGD, which is equal to 180 degree minus angle GCD minus angle GDC. Again, by the similar logic, angle GCD is half of angle C and angle GDC is half of angle D. So now when we add angle FEH plus angle FGH, that is equal to 180 degree minus half of angle A plus B plus 180 degree minus half of angle C plus D. So this is equal to 360 degree minus half of the sum of all the four angles. But we know sum of all the four angles is 360 degrees. So 360 by 2, that means 180 degrees. So 360 minus 180 degree is 180 degree. Hence we have shown that the two opposite angles FEH and angle FGH, the sum is 180 degree. Hence EFGH is a cyclic quadrilateral. Another interesting example. A chord of a circle is equal to the radius of the circle. Find the angle subtended by the chord at a point on the minor arc and also at a point on the major arc. Now what is given to us is the chord AB. There is a chord AB which is equal to the radius. Suppose OA and OB, they are the radii of the circle. So you have chord AB, radius OA and OB, all three are equal. Hence triangle OAB, it will be a equilateral triangle. So all the three angles will be 60 degree. Hence angle AOB is 60 degree. Now recall an important theorem, theorem 9.7, which says that angle subtended at the center is double the angle on any other point. So AOB is the angle subtended at the center. So AOB is 2 times ACB. That means ACB is half of angle AOB, which is equal to 30 degree. So we have got that angle ACB is 30 degree. Now ACBD, it is a cyclic quadrilateral. Why? Because all the vertices lie on the circle. So the opposite angles of a cyclic quadrilateral, the sum is 180 degree. So angle ACB plus angle ADB, that is equal to 180 degree. So but angle ACB is 30 degrees. So angle ADB is 180 minus 30, which is 150 degree. So we have got angle ADB, which is equal to 150 degree. That means the angle subtended by the chord at a point on the minor arc and also at a point on the major arc. We have found for both of them. For the minor arc, it is equal to 150 degree and for the major arc, it is 30 degree. Now example 9. ABCD is a cyclic quadrilateral whose diagonals intersect at point E. If angle DBC is 70 degree, angle BAC is 30 degree, find angle BCD. Further, if AB and ABC are equal, find angle ECD. Now first of all, if we consider the chord CD, from the diagram we can see that angle A and angle B are on the same side of the segment. We know that angles in the same segment are equal. So since angle DBC and angle CAD are in the same segment of the chord CD, both are equal. But we are given angle DBC 70 degree, so angle CAD will also be 70 degree. Now angle BAD, that is equal to angle BAC plus angle CAD. So that will be equal to 30 degree plus 70 degree, which is 100 degree. So we have got angle BAD, which is equal to 100 degree. But this is a cyclic quadrilateral, all vertices are on the circle, it is cyclic. So we know that opposite angles of the cyclic quadrilateral sum to 180 degrees. So angle BCD plus angle BAD, sum will be 180 degree. but already angle B.Ed is 100 degrees, so angle BCD is 80 degree. So we have first obtained angle BCD, which is equal to 80 degree. In the second part, it is given if AB and BC are equal. So consider triangle ABC in which AB is equal to BC is given. So angles opposite to equal sides are equal. So angle BCA and angle CAB, both of them are equal. So angle BCA will be equal to 30 degree. But angle BCD is 80 degree. So what is angle BCD? BCA plus ACD. That is equal to 80 degree. Hence angle ACD is 80 degree minus angle BCA or minus 30 degree, which will give you 50 degree. So hence we have obtained that angle ECD is 50 degree. Example 10. Prove that a cyclic parallelogram is a rectangle. So suppose we are given a cyclic parallelogram ABCD, means all vertices are on the circle. We have to prove it is a rectangle. In rectangle, you know that the angles are right angles. So now first of all, since it is cyclic, we know that the sum of the opposite angles is 180 degrees. So angle A plus angle C is equal to angle B plus angle D, which is equal to 180 degree. But opposite angles in a parallelogram are equal, correct? So since it is a parallelogram, the opposite angles are equal. So angle A and angle C will be equal and angle B and angle D is equal. Hence we have that angle A is 90 degrees. Similarly, we can prove all the angles are also 90 degrees. So ABCD is a rectangle. Example 11. ABC and ADC are two right triangles with common hypotenuse AC. Prove that angle CAD is equal to angle CBD. Now here we have two right angle triangles with angles B and D both 90 degrees. AC is the common hypotenuse. We need to prove angles CAD and CBD are equal. Now we know that B and D are right angles. As angles in a semicircle are right angles, the triangles ABC and ADC will be in the same semicircle, and so points ABCD are concyclic. Now CD is the chord of the circle. So by theorem 9.8, angles which are in the same segment of the circle are equal. So angle CAD and angle CBD, they are in the same segment and hence they are equal. Some objective questions. Fill in the blanks. The center of a circle always lies in the interior of the circle. A point whose distance from the center of a circle is greater than the radius, obviously it will be in the exterior of the circle. The longest chord of a circle is the diameter, you know this. An arc is a dash when its ends are the ends of a diameter. So an arc will be a semicircle if its ends are the ends of the diameter. Segment of a circle is the region between an arc and chord of the circle. The circle divides the plane on which it lies into how many parts? 3 parts. Circle, its interior and exterior. True or false objective questions. Line segment joining the center to any point of the circle is the radius of the circle. This is true. A circle has only a finite number of equal chords. This is false. If a circle is divided into 3 arcs, each is a major. No other will be minor. A chord of a circle which is twice as long as the radius is the diameter. Yes, diameter is always twice the radius. Sector is the region between the chord and its corresponding arc. No, that is false. What is the definition of sector? It is the region between two radii and the arc. And segment means it is between a chord and the arc. So be clear with this. Sector is the region between the chord and its corresponding arc is false. Why? Because sector is the region between two radii and the arc. A circle is a plane figure. That is true. Some assignment examples. Please do solve these assignment examples. They will give you a lot of practice. First one, we know that two circles are congruent if they have the same radii. Now prove that equal chords of congruent circles subtend equal angles at their centers. The proof of this is similar to the proof of theorem 9.1 which we have seen. Second part, prove that if chords of congruent circles subtend equal angles at the center, then the chords are equal. Again, this is same as 9.2 converse. Find the length of a chord which is at the distance of 5 cm from the center of a circle and of radius 13 cm. The answer is 24 cm. The lengths of two parallel chords of a circle are 6 cm and 8 cm. If the smaller chord is at a distance of 4 cm from the center, what is the distance of the other chord from the center? The answer is 3 cm. We have done a similar example. Assignment example 5. In the given figure, A, B and C are 3 points on a circle with center O such that angle BOC is 30 degree and angle AOB is 60 degree. If D is a point on the circle other than the arc ABC, find angle ADC. The answer is 45 degree and the hint is use theorem 9.7. Sixth one, in the given figure A, B, C and D are 4 points on the circle. AC and BD intersect at a point E such that angle BEC is equal to 130 degree, angle ECD is 20 degree. Find angle BAC. The answer is 110 degree. The hint is we know that angles in the segment of the circle, same segment of the circle are equal. Assignment example 7. If the non-parallel sides of a trapezium are equal, prove that it is cyclic. So first of all, draw the trapezium ABCD, draw perpendiculars AM and BN to CD, and by RHS congruence first you will be able to prove that triangles AMD and BNC are congruent, and then by CPCT you will be again able to prove the result. Two congruent circles intersect each other at points A and B. Through A, any line segment PAQ is drawn so that P and Q lie on the two circles. Prove that BP is equal to BQ. Please draw the diagram. The hint is sides opposite to equal angles are equal. So accordingly you will be getting the proof. Ninth, if diagonals of a cyclic quadrilateral are diameters of the circle through the vertices of the quadrilateral, prove that it is a rectangle. The hint is we know that angles in the semicircle are equal. On the basis of this you will be able to prove it. In case of any query for the assignment examples, please write in the comment section. Circles is a very important chapter with many results and proofs and examples also. So please practice them. Do like and share the video and subscribe to the channel for many such other videos for class 9th and 10th maths. Thank you.